Good morning, everyone. Can everyone hear me? And is the video coming through clear? Make sure to say so in the chat. Some sort of confirmation that you can hear the audio okay. Perfect. Good morning, everyone. Okay. So again, keep it excellent. Yes, it's just a white piece of paper at the moment. I haven't written down anything yet. Just getting the pen ready. And so this is lecture 2. And what we're doing today is population, well, we're going to be covering a couple of sections today. So I'm going to call this Descriptive Statistics. Okay. And today's the 13th of January. So again, this is 209. Probability and Statistics. My name is Richard Kohar. And for those that are in the class or attending it at RMC, these notes will be made available through Moodle after the class is finished. Okay. So, the main reason why we're all here is because of data. And what data is that it's a collection of related facts. Data is something that we measure, we collect, we report, and we analyze. There's two concepts that we kind of apply with data. And these words have slightly different meanings than our ordinary usage in our everyday life. But close enough that it should be straightforward. So let's suppose, I'm just drawing this box here as best as I can. So suppose that I have a population of people. And let's say that here's the entire population. I kind of quite a few stars there. Those could be people, they can be anything. So what a population is that it's the entire collection of objects being investigated. Can use being investigated, of interest. And the other thing that we have is something called a sample. And that's where we could pick something like this. Here's a little box. So I have 2 stars. And this is what we'll call a sample. Okay. And a sample is then just some of the objects selected from the population. So you can see that we're looking at, when we talk about population, we're talking about all the objects that we're interested in. And when we say that we have a sample, then it's some of the objects. So again, these are terms that we have in everyday life. We can think of a population of a country. We can think of a sample where, oh, look, a nice plate of cheese, or samples that we go to, they'll call them samples when we go to Costco or something like that. They have little sticks. So all of this is then the population of cheese that I'm interested in. And this is one that is, this is a sample. I'm going to have 1. And here's another one. I've picked 2. So 2 pieces of cheese. There's the sample. And I can tell you it is delicious. All right. Oh, and by the way, I might as well. Here's a population of coffee. And I'm going to take 1 sip of that, and that's going to be my sample of it. It's a light roast. Coffee is always good for doing math. As one very astute observer once said, that mathematicians are simply persons who turn coffee into theorems. So here's an example. We have a population, and again, the idea is of the entire objects, or the entire collection of objects being investigated. So for instance, we can think of like the 2021 the Canadian census, we collected detailed information. So people had to submit detailed surveys. If they didn't, there was also people who went door to door. And this was about the entire Canadian population. With a reference date of the 11th of May. Okay, the second one is here's an example where we kind of do like maybe an investigation into, say, all students and let's say who received a degree. An undergrad degree in engineering at RMC. Okay. let's say that I also have some examples then for doing with other data. So for instance, we had gone through a federal election last year. So in the federal election, there is an opinion poll. Lots of them that were done during the election. They're conducted by surveyors. And they randomly select, say, 1,000 people. And they phone them to ask questions. So again, instead of surveying or looking at getting the opinion of all of the population of Canada, they pick a subset of them. 1,000 people. We have around 33 million people, so 1,000. Is some of the people of Canada. You could also select, say, 10 bullets from 1,000 rounds, and you can test to see if they're defective. So notice, for instance, that I was interested in them being defective. I want to make sure that whatever I'm buying is working properly. I want to basically what this is I'm interested in the characteristic of the bullet or the object of interest. So when I'm interested in something like this is what we'll call a characteristic. Okay, so we have characteristics. And they kind of fall into two classes. We can have numerical, and we can also have categorical. Under numerical, I could be interested, say, in the age of students. I could be interested in the, let's say, diameter of a ball bearing. And I could also be interested in the lifetime of a battery. And so associated with each of these, we'll have what we'll call a value. So like the age of a student could be 19 years old. The diameter of a ball bearing could be 10 millimeters. Lifetime of a battery, 10 hours. I would say it's quite common when we're thinking about numerical characteristics that there's a value and there is an associated, there's a number, and along with it is a unit, a measurement. The other one that we can do is categorical, and that's where they're kind of, well, it's probably best illustrated with examples. We could say types of malfunction. And, you know, at types of malfunction, it might not have a numerical value to it. Instead, we could give it maybe, like in this case, types of malfunction, we could just give it binary. We could just say that it's either defective or non-defective. I could talk, say, a brand of clothing. So you could have, say, Gucci, Armani. Too many I's at the end. Let's use Burberry. So again, those aren't numbers. Those are the values. We could also talk about things like educational level. We could be saying that it could be elementary. So say when we're surveying people, for when we're talking about the census, they could be asking the educational value, level, the highest that they've attained. Elementary, we could say high school, university. So that is, we're always kind of usually interested in some sort of characteristic of the things that we're investigating. Now let's also discuss then what a variable is. So we have a variable. And that's is any characteristic whose value may change from one object to the next. And probably, let's say, inside of a population. Okay, so again, we'll give some examples, lots of examples to make sure that cement this. So let's say X, and it could be that it's the brand of a cell phone. Owned by a student. Let's say we could do Y. Number of calls dropped. Let's say by communications. Sorry for joining. Okay. Dropped by a communications provider. In a specified interval. Specified. time interval. And I don't know, let's something interesting. Let's go especially during the winter time. Let's say the length of skid mark of an automobile let's say attempting to stop, of course. And let's say down Fort Henry Hill. We could do V, and again, I'm just, let's say the number of views. Of a TikTok video. On a particular account. And we can keep going on and on and on and on. Okay. So we've talked about characteristics, that they can be either numerical or categorical, and that a variable is any characteristic whose value may change from object to object, and that's what we're interested in. So a variable can be, we could have a univariate. So uni meaning one. So in this case, I could say the data could look like, well, let's talk about brand of cell phones owned by a student. So we could say Apple, Google, Motorola, Google, Apple, so on and so forth. And so this is an example of categorical, where we have A for Apple, G for Google, and M for Motorola. We can have a bivariate. And again, bi meaning two. So instead of having just one piece for each kind of object, you could have two pieces of information for each object. So let's say if we think of a person, we could have, let's say, 72 and 168. Over here I could have another one, 75, and this is 212. And let's say that this is the height in inches, and there's the weight of a person. So we could collect both weight and height and associate it with one person. And in the chat, can you tell me what kind of characteristics is for this? Is this categorical or numerical? And we'll just kind of wait in the chat there. Yes, it is numerical. Excellent. Good. I'm also getting to see how much lag there is. So it's not too bad today. There's maybe about 10 or 15 seconds. And so we go 1, 2, and then many. So we'll go multivariate. And that's more than one. In that case, I can do 120, 80, and 70. And so in this case, I'm thinking of a patient. Let's say this is this systolic. We can have the diastolic. And then the heart rate measured in beats per minute. Okay. So having obtained a sample from a population, an investigation draws a conclusion or makes an inference about the population. What inferential statistics, which we'll be getting into later, it deals with a question of extending to the entire population some feature that was observed in a sample. So let me just kind of rephrase that. Let's say that I have a sample that I've collected from a population. So what what statistics is doing is when we sample, we're trying to infer, again, from this sample, saying that whatever conclusions we make holds for the entire population. And so that is what they'll call inferential. They're making an inference. And I like to think of this as inductive reasoning. So again, I have a collection of pens beside me. I have, well, here's a blue pen, and here's another blue pen, and here's another blue pen. And from this, I would conclude then that the entire collection of pens that I have, my population, which is, let's say my pens that have, those are the things that I'm interested in, I will then say that they're all blue. And that, you know, may be fine. Most of my pens seem to look blue. But of course, that's not true because I have many other colors. I can have a purple, I have pink, yellow, green. So, in statistics, it gets very important when we consider the sample. We want to make sure that the sample is representative of the entire population. And people can spend a lot of time trying to devise a way of sampling something. Say either using random sampling or random sampling or clustered sampling or sampling at specified intervals. So we're trying to avoid kind of, we're trying to infer about the entire population. Now the other way, which is using probability, I call this more like a deductive kind of. In a probability problem, the population characteristics are known. So we know everything about the population. So I could have a collection of pens. There's a collection of pens. And then, so I know the entire population, and I can then, I know almost what my sample will look like. if I randomly select, I can calculate what the probabilities of picking those pens were without absolutely knowing. So maybe I'll just recap that. I'm not sure what the ribbon means. So with the probability problem, yes, that's a good question. Somebody is asking, when you say multivariate, you describe it as being more than one, while bivariate is described already as being two. So does multivariate include things that are bivariate? And the answer is yes. So you can think of a bivariate as also multivariate as well. But what I can say then is we give it a special term. Why do we call it bivariate? Is that we do have data that groups into two like that so often that we do in fact give it a special name. Now, like for instance here, we may be quite interested in things like this when we get to, let me just take a second. When we want to do a statistic like this, we may be interested in doing the BMI, which is the body mass index. And just a second, I will double check it. So what we usually do then is we do the weight over the height squared. Now this is usually though in kilograms, and we usually think of this in meters. So this is, I wouldn't start calculating the BMI yet using the height in inches and the weight in pounds. We'd have to convert that. But again, this would be data about a particular person, and then we're going to perform some sort of statistical analysis like using BMI, and we can reduce it down to one number. But it's, again, like I said, it's common enough that we give it a bivariate a name. Okay, good. So probability. So the entire population is known. And then questions about taken from the population must be then fixed and well posed. Okay, and with the statistics problem, is used. to infer about the entire population. Just switch over here. Okay. So now we're going to move on to section 1.2 in the textbook, which is pictorial and tabular methods in descriptive statistics. And the first thing they want to do is talk about stem and leaf plots. And just a little bit of opinion. Again, things change in the course of mathematics and statistics. And in particular, stem and leaf plots, in my opinion, are outdated way of displaying data. It was developed in the 70s when typewriters were common, and we prefer displays and plots now since we have access to digital computers and phones, and they have great plotting capabilities now, and we can make graphs and pie charts and many other things easily without having to resort to this older style of display. But they, might be still useful for some people. They work well for relatively small sets of data, and it displays things like the location, the spread, the extremes, and the gaps in the data. So here's an example. The weights to the nearest tenth of a kilogram of 30 students were measured and recorded as the following. So here's a list of all of the data. And very typical of a typewriter, I hit the wrong number, and so I backed it up and wrote over top of it. So what we are asked then is to prepare a stem and leaf plot for the data and briefly comment on what the analysis is. Okay, so stem and leaf plot. So the idea is that we pick something where the stem, it doesn't change. Okay. So I'll just kind of draw this vertical line here. And I won't have to label this explicitly all the time, but let's say that this is the stem. And here are the leaves. And so what I can do is I can look here. I see that my lowest here is okay, so the lowest I see is 56. Okay. And the highest that I saw was, so 56 was the lowest. And let's look for the highest. I think the highest here is 65. So we have our stems. We have 57, 58, 59, 60, 61, 62, 63, 64, and 65. So what I can do is I know, let's say here 56.3, and this then becomes my leaf. Maybe I might put a little dot after here just to say that this is my 10th decimal place. And again, you just work through the entire data. And so there's no 57s in here. There is 58s. There's 1, 2, 3. So I have over here 58. So there's 4, 4, and 9. Now I'm going to speed this up a little bit because time is the essence. The other reason why people may enjoy using these is that, again, you're watching me write out the data, is that it might be useful for when you're actually collecting the data. And you can already see visually as you're collecting the data or as you're filling this in, the distribution of the data. So it might not necessarily be great for using it in a published report, but it might be useful for exactly what I'm doing here, writing it out by hand. So again, in this example, we can see that the largest group with the highest number of observations is recorded between 61 and around here. We can see that this was the biggest amount. And there it is right there, written out. Any questions about that so far? And so just to review again, constructing a stem and leaf plot, just select one or more of the leading digits for the stem values, and the trailing digits become the leaves. You list the stem values in a column, and you record the leaf for each observation beside the corresponding stem value. And then you should somewhere indicate the units for the stem and leaves someplace in the display. So let's put down here that this is in kilograms. So we kind of understand that it's kind of clustered around between 58 and 62. So we kind of know what the location is. We know how much spread there is. We can see the extremes, which is the lowest value and the highest value. And we can also see some gaps in the data as well. Okay. Of course. We're on to page 5. That won't go too far away. We'll keep using that example. So the leaves are just possible decimal places of the stem numbers. Yes. They don't necessarily have to be decimal places. Basically, we're looking for numbers that are kind of consistent. So just as something else, I could say something like the number of miles, or sorry, let's say the kilometers travels by a car out of rentals, and we can see the trips. We could say it's 301. We could do 310. We could do Okay, so the way that you could do this is I'm looking for things that are, let's do a couple more then. Okay, so what I'm seeing here is I'm getting a lot of repeated digits, say in the first, two decimal, or the first two places. So I'll do, say, 30, 31, 32. Up to 40 here. So again, here's 1, 31, here's the 0, I have 31 and 50, there we go. There's a 6, 32, okay, so there's the 1, I have 0 here. So that would be like the stem and leaf plot for this collection of data here. And so you can see that it's not necessarily about the decimal places. We're just looking for things that are common. So I have two pieces of data where I had basically 300. I had three pieces of data for the 310s. And again, it gives us a quick way of collecting data, perhaps. We can also see the extremes, we can see the gaps in the data, and we can see the spread, the location as well. Okay, so I hope that helps. Now here's another one, is that we have a dot display. Let's say dot plot. So a dot plot displays each observation as a dot. Above some the corresponding location on a horizontal measurement scale. Okay, and if it repeats, there's a dot for each occurrence. And the dots are usually stacked vertically then. Okay. So if I want to go back to this data here that we have with the weights and measurements, what I can do then is convert this to 5. Grab another piece of paper here. Okay. So let's do the dot. The dot plot for the example of 30 students. Okay. So I'll just write down, here's my horizontal scale. And so what we would do is we just look at the number of times that it shows up. So there's once where we have 56, we have 358s, 1, 2, 3. There's 5 59s, 1, 2, 3, 4, 5. There's 1, 2, 3, 4, 5, 6, 7. 2, 4, 6, 8, 9. 1, 2, 3, 4, 5, 6. There we go, 9. 4. And one more. So the idea is to try to make sure that the dots are equally spaced as well. And again, it kind of gives you a distribution. And again, similar to what we saw with the stem and leaf plots, you can see gaps in the data. You can see the extremes. You can see where the data is clustering. We're getting more into the more conventional things that we're used to seeing now. Histograms. And before we get to that, let me just take a little moment to mention that these can be constructed either for continuous or discrete. Continuous variables. And let's just take a brief moment to discuss what discrete means. So it means that it's either finite meaning that there's a specific number of them that's less than infinity, or can be ordered or listed in an infinite sequence. By that I mean it's one number after another. Okay, so, but I've already seen these number systems before. For discrete, we could have natural numbers. So these are the naturals. And that starts out with 1. And they're also known as the counting numbers. So that's an n for the naturals. We can have whole numbers. Those are the whole numbers. And again, that's basically the naturals with 0. We can have integers. And basically those are natural numbers and 0, and also allow them to be negative. So we can have -3, -2. These are what we call the integers. We have Q for rationals. Q also was picked because of the word quotient from Italian. And Z was picked because it means number in German. But the rationals are quotients, or you can think of them as fractions, the fractional numbers. So they're fractions, and those fractions are, let's say, any number m and n, such that m and n are in the integers, and that we can't have that denominator equaling 0. So let me just write that out in words, because some people might not know the set notation yet here, but this is m and n such that m and n are integers, and n cannot equal 0. So these are discrete numbers. And over on the right-hand side here, we'll use continuous. So continuous, we have the reals. And the reals are made up of everything. So it includes all the discrete numbers here, but it's the rationals and the irrationals. So over here, I can draw, say, a number line. We'll go from 0, let's say 1, and here's 2. And here's an example of an irrational number, which is square root of 2. And that's a number, square root of 2 is a number that we can't express as a fraction. So let me just make a little small note. Sometimes our instruments may be limited in precision, but it might be easier sometimes to consider the measurements as continuous rather than discrete, simply because it may be easier to work with a continuous model. So the measurement instrument. Is finite. Okay. Okay, let's move on for a second. So here's number 7. We're going to talk about frequencies of discrete data, or for discrete data. So what we can do is we can consider data that consists of observations. So on a discrete variable x, okay, so let's get back. It's now 9:14. So we're going to talk about frequencies for discrete data. Consider data that consists of observations on a discrete variable. So we will talk about the frequency of a given value x is the number of occurrences in the data set. And then we also have relative frequency. What that is it's the proportion or the fraction in the data set. Okay, so we go back to, so maybe I can write out that. So some people, so there's relative frequency so it's the number of occurrences of the value over the total number. Okay, so what we can do is So using the example of the students' weights that we were looking at, well, in this case, X would be the weight of the student. So if there was 59.0 and it occurs twice, then the frequency of 59.0 is 2. And the relative frequency is there's 2 of them out of 30. Or you can view it as 1/15, which is approximately 0.0667. Okay. If you multiply the relative frequency by 100, this gives you, or gives a percentage. So again, if I just multiply that by 100, therefore, .67% of the students in the sample are 59 kilograms. Okay? So moving on to an example. Here's an example. So there's Peter Norvig. He's a computer scientist who currently is the director of research at Google, and he's known primarily for his research in artificial intelligence and also NLP, natural language processing. Google Books is kind of this ambitious project that is trying to digitize all of the world's books. And so as of October 2015, it had scanned more than 25 million books, and that gives you approximately 10 billion pages that have been digitized. And to kind of give you that idea or the scale or the magnitude of this kind of project, the United States Library of Congress has 32 million books. So if Google Books had started with the Library of Congress, it'd be about 78% done. So in 2012, while going through the massive 23 gigabyte Google Books dataset, Dr. Norvig compiled several tables, including this frequency of word lengths in the English language. And what we have here is the frequency of word lengths. So, a word length of just 1, there's about roughly And then the frequency, again, is huge. It's in the millions. 22,301 million. And it gets kind of peaks around, let's have a look here, around 3, so 3 letters. Also, just kind of as a remark, just because of 3, the most common word in English is the, which accounted for about 7.4 or 7.14% of all the words in Google Book data. Okay. So again, this is the frequency, and it's in millions. And so let me just show you. So I have the frequency, and to get the relative frequency, what I would do is I take the number of occurrences, and I divide it by the total number in the data set. So that's what I've done here. I've taken having a look at this, I've taken the number of frequencies, so here it is over here, and we divide it by the total amount. And we can actually then say that these are the relative frequency. For, say, a word length of 1. And I've worked it all the way to 23. Oops. And let me just show you the plot then of that. So here's what you could think of it as a histogram, but we can plot all this data. So as we expected, you can think of this as the relative frequency. And over here is the word length. And so for here, 1, we've then plotted it with around 3%. And for 2, I've plotted it around 20%. For 3, it gets even bigger. It's around 20%. It drops down for 4, down to 14. So the reason why I'm kind of picking kind of lines and points is because these are very specific. It is for just 1, 2, 3, 4, 5 exactly. So sometimes you'll see people, such as myself, that will actually use lines as opposed to making bars and connecting all the bars together. What I would say is that the book goes through great detail about constructing histograms, etc., etc. But I will do an example, but I do suggest going through the textbook and reading through how they construct it as well. But what I can do is I can show you for discrete let's go back to that example of, oh, not necessarily this one, but let's go back to the stem and leaf plots. And so what I will do is, let's use a new piece of paper. Okay. So here's that data again. So we're going to have to go from 56 to 65. And I'll do the same thing. I'll just now again, there's lots of plotting packages now. You don't have to do stuff like this by hand as much anymore. But let's say 56. And here we go up to 65. Okay. Okay. And the other thing I need to do here's the relative frequency. And it needs to go up to, let's see. Okay. So what I've done is I know that the most I have is 9. And so I'm going to go from 0 to 1, 2, 3, 4, 5, 6, 7, 8, 9. So I can do 1, 2, 3, 4. Okay, but again, that's not the, if I just did that, that's the frequency. If I want the relative frequency, well, then I need to also divide by the total number. So I know that there's 30 students, so 1 out of 30, 2 out of 30, 3 out of 30. Okay. And so I can just work through here. Maybe the easier way. So the first one I have is 56. I know that I only have 1. So up to this part right here. There's my first bar. I have 58, so there's 3 of those. There's 58, 59. So in this case, there's 2, 4, 5. 5 here. Two, 4, 6, 7 of these. Okay. Has anyone had to draw histograms by hand before? Maybe perhaps in a lab setting or during a lab at school, you had to draw out some histograms. Yes. Yeah. In grade 4. There's 2. And I'm almost done. I have one last one, which is 1 over in 65. Okay, so there is my histogram of using that stem and leaf plot. Well, using the data that we had here with the 30 students. So there's some people that may shade them in to kind of give it. That's a good question. There's some people. Do the data bars have to be stuck together? Is this the only acceptable histogram? Yeah, I would say that histograms traditionally are stuck together. So yes. Now, what I would like to say, though, is that it's very similar to English or any other. If you are going to publish or you're going to follow, what I would say is that if you are going to do any kind of publishing, or you would basically, this comes down to style. So I would say, whenever you're doing something, check the style or the style book for your publishing guidelines. So what I mean by that is that there's different publishers that they will tell you, for example, like there's commas. We could put commas after every object in a list. which we call like the Oxford Comma, and that those are called things like style. So those are things that are prescribed by the person that's putting together the publication. So I'm going to say the same thing about visual language as well. Most of the histograms that I've seen are usually stuck together, but some people may say they want a space in between it. If there's a space in between it, then they usually call them bar graphs. Okay. I think that's all that I'd like to say about histograms, because I think they're pretty straightforward. The same idea. I can see the extremes. I can see the gaps in the data. I can see basically the location or how much it's spread out in the data. Okay. What more? Here's number 11. Here's number 12. So what we were looking at was kind of like the distribution of our data. And when you look at these types of features, or when we're just looking at the distribution, we can see the number of peaks, we can see the general shape, we can see the center, the spread. So the first characteristic that we can readily see from something like a histogram is the number of high points or peaks that the distribution has. And most distributions that occur in statistical data have only one main peak. And so in this case, we see that there's one main peak and it's 61. And when we see that there's only one peak, we call this unimodal. And other distributions may have two peaks, we call those bimodal. Or if there's more than two peaks, well, then they start to call them multimodal. So again, let me give you, we can talk about so we have the number of peaks. So let me just kind of So we can have one peak, so something like that. Oops, unimodal. So that has one peak. We can have two peaks. So again, that's roughly the same. So this is called bimodal. Here's two peaks. And we can also have multimodal. Have things like the general shape, and so we can either have this as symmetric or we can have it skewed. So again, so there's symmetric. And basically we can almost even draw a line of symmetry. So this is symmetric. There's the line of symmetry. And if the distribution is lopsided, it's said to be skewed. So we say that a distribution is to be skewed to the right or positively skewed when most of the data is concentrated on the left of the distribution. And distributions with positive skews are more common than distributions with negative skews. So let me just so this is called right skewed. Or positively skewed. And that's where the data is more toward the left. and these are more common. Than left skewed. So I should also then draw what the left skewed would look like. And the data is to the left, or sorry, is to the right. And these are less common. Okay, well, I think this is a good spot to stop. We've now hit the end of our lecture period. If you have any questions, feel free to send me an email at my RMC account, and I will post these lecture notes on the Moodle webpage. Thank you everyone for participating in today's lecture, and again, feedback is always welcome and appreciated. All right, I'll see you all on Tuesday. Thank you everyone. Take care.